Okay, ladies and gentlemen, in this video, I just want to tie up some loose ends before we leave circuits for a little while. And here, the only loose end that we've had is we've worked with circuits that had combinations of resistors in series and parallel, but we started with the idea of a capacitor, and we never closed the loop on how those things function in a circuit if they're combined in series and or parallel. Now remember, in this class, we're never going to deal with combinations of capacitors and resistors, so this is just capacitors when they're linked together in either series or parallel. The definition of series is still the same thing, back to back, parallel still being the same thing when you have a choice as for which way the current, or in this case with capacitors, the charge goes. So this video will be pretty short, going through how this looks. Big question for us to think about in the beginning, are they going to behave exactly the same way as resistors? Maybe, maybe not. Give it your thoughts before we start jumping into it right now. Okay, so here's a picture of capacitors. Remember, capacitors as circuit elements are represented by two parallel plates of the same length of line. That way we don't confuse them with batteries, which has the shorter terminal and the larger terminal. So here we see two capacitors in series and two capacitors in parallel. And we want to develop the rules as to how these things combine in either series or parallel in the exact same fashion, using the exact same rules that we did for resistors. Namely, we know that if we're going to get from point A to point B in series, then everything that flows through the capacitor, these are friendly capacitors, has to get through C1 and then get through C2. In parallel, when we have a choice, some of the current goes one way, some of the current goes the other way. Again here, current, remember, is related to charge, and charge is what's important for capacitors. So in the parallel combination, some of the current goes one way, some of the current goes the other way, but either way, we still end up starting at the potential difference from A and getting to the potential difference in B. So whether we go through the C1 path or the C2 path, we've only paid one price, okay? Those are, again, the same rules that we did for resistors, and those are gonna be the same rules that we're gonna use in order to set this up in solving how it adds or combines in series and parallel. So let's start the same way that we did with resistors. We'll do it first for those in series. And let me remind you, the basic definition of capacitance is charge over voltage, okay? And so here, we know if we have 2 points A and B, there's a potential difference between A and B. And for the series combination, let's put a point, well, C is probably a bad name. If we don't want to confuse it with capacitance, let's put a point D in there, right? That to get all the way from A to B, we first got to go through A to D and then from D to B. But what do we know? We know that if C1 is a capacitor, this has to be true. And if C2 is a capacitor, this has to be true. But we said these are friendly capacitors, so what do we definitely know? Q1, everything that goes through 1 has to go through 2, and so that we can just call overall Q total, okay? By the same token, V total is the potential difference it took to go from A to D, plus the potential difference to go from D to B. Namely, we made 2 stops, we had to pay 2 prices, okay? In going from A to D, all that we do is go through capacitor 1, and in going from D to B, all we do is go through capacitor 2. So if that's the case, let's use the definitions of C1 and C2 to instead write it in terms of V1 and V2. If that's the case, then what we see is V total is also known as Q1. Well, let's just spell it out. That way everybody's with me on the algebra here. V1, by this definition of capacitance, is going to be Q1 over C1. V2 is going to be Q2 over C2, which means that V total then is Q1 over C1 plus Q2 over C2. But remember the fact that we said that Q1 was equal to Q2, which is the same as Q total. So let's make that replacement right now. That means that V total is also known as Q total over C1 plus Q total over C2, which another way of saying that is I can factor out the Q total and I get 1 over C1 plus 1 over C2. And we see something happening here. This is starting to look very familiar to how we did it with resistors. But if we want to get this in terms of capacitance, we know a capacitance is a charge over voltage, okay? So if we divide both sides by the charge Q total, then we see that VT over QT is 1 over C1 plus 1 over C2. But remember that since QT over VT would be the total capacitance, then it serves that VT over QT is 1 over the total capacitance. And what do you know? We see a very familiar formula emerging, namely the 1 over the C total is 1 over C1 plus 1 over C2. But this now is for capacitors in series. Namely, capacitors in series behave just like resistors did in parallel. So if we want to know the total charge of two capacitors C1 and C2, and we place them in series, we could have replaced them with a capacitor CT that goes by 1 over C2, CT is equal to 1 over C1 plus 1 over C2. The exact opposite of resistors in series, which if you remember, resistors in series added like the following. So with having said that, is it going to be the case then that resistors and capacitors in parallel happen to behave the same way as resistors in series? Let's see. So if we scroll back up here, once again, what's the main rule that we're going to exploit is that no matter which one we go through, actually we get a choice. Some of us go through C1, some of us go through C2, but either way, you only went through one thing. So therefore, we know that V total is the same as V over AB, which is the same as those who went through 1 and those who went through number 2. Namely, you only went through one object to get the total potential. If that's the case, before we solve these for C1 and C2 for charge and capacitance, so let's do the exact same thing. But what else do we know? We know that at the junction, right, charge has to be conserved. So Q total has to be Q1 plus Q2. The amount of charge that goes to 1 plus the amount of charge that goes to 2 has to be the same as the total charge that entered the system, because again, these are friendly capacitors. So if that's the case, let's use the definition for C1 and C2 and solve it for Q1 and Q2. So again, since C1 is Q1 over V1 and C2 is Q2 over V2, that tells us that Q1 is just C1 V1 and Q2 is C2 V2. But remember, we said that V1 and V2 is the same as V total. So if we use that in this formula up here, namely conservation of charge, then we see that Q total has to be Q1 plus Q2, which now we make the replacement C1 V1 plus C2 V2, but we make the replacement that V1 is the same as V total, which is the same as V2 V total. And what we get here is we can factor out a V total. And again, we see something very familiar emerging. If I then divide both sides by the total voltage, I see that QT over VT is equal to C1 plus C2, but by definition, a ratio of charge to voltage is nothing more than a capacitance. So if it's the total charge over the total voltage, this is the total capacitance. And what do you know? For two capacitors in parallel, they add very simply. C1 plus C2 could have been replaced with CT. Again, the exact opposite rule for resistors in parallel, which was 1 over RT is equal to 1 over R1 plus 1 over R2. So if we take a look back then and summarize these two formulas in boxes and compare them to the ones that I'm about to put in a red box, we literally see that we can take what we already knew about resistors and how they combine in series and parallel. And by the same rules that got us there in the first place, we see that the rules for capacitors adding in series and or parallel are the exact opposite rules. So if we could do it for resistors, we can now do it for capacitors. All we have to do is just change our brains around and say, aha, what was series now becomes parallel, and use those rules, and we'll be able to find those net capacitances instead of the net resistances. It's as straightforward as that. That's the last loose end that we had to tie up in this topic of basic circuits. And so, yeah, there'll be a couple of problems that we'll explore during the week and in your homework about adding capacitors in series and parallel. And again, it's the same thing that we've already done, except that the picture changes to make them capacitors instead of resistors. We literally just switch the rules from series to parallel, and we'll be in great shape. It really is as simple as that. As always, ladies and gentlemen, if there's questions, comments, complaints, or concerns, please don't hesitate to ask. I look forward to seeing you soon, and have a great weekend.